Assalamualaikum everyone. Today we are focusing our project on Mami Double Decker, a household brand established back in 1971 that currently exports its iconic snacks and instant noodles to over 100 countries worldwide. However, mass producing such a wide variety of goods come with heavy logistical challenges. Their daily operations are limited by shared machinery, workforce hours and strict factory resources. If resource planning is not precise, it quickly leads to production delays, inflated operational costs and ultimately unhappy customer. To tackle this, our project applies linear algebra and matrix modeling to optimize their resource allocation and streamline their entire production planning process. Moving on to our problem statement, Mami manages six core products represented as variables X1 through X6, which include favorites like Mami Monster, Mr. Potato, Mami Chef and Double Decker. The production of this item is heavily constrained by four major bottlenecks, which is machine operating time, heat processing capacity, seasoning capacity and limited packaging space. This sets up a system of four resource equations but with six product variables. Because we have more variables than equations, this forms an underdetermined system, meaning there are infinitely many feasible production solutions. To navigate this, we apply Gauss-Jordan elimination to find reduced row echelon form, allowing us to isolate free variables and find the most efficient production mix.
Assalamualaikum, I'm Faris, number BTT137721. This presentation demonstrates a comprehensive linear algebra workflow beginning with a system of four linear resource constraint equation configured to optimize a factory production schedule for snacks like Mami Monster and Mr. Potato. To solve this, we convert the system into an argument matrix and meticulously apply Gauss-Jordan elimination of a series of row, swap and systematic elimination until achieve the RF, which was cross-checked using MATLAB to ensure absolutely numerical precision. A rigorous consistency analysis confirmed that because the rank of matrix A equal the rank of the argumented, a realistic and viable production schedule exists. However, because column 5 and 6 lack leading pivot, we identify two free variables, gesturing and instant noodle, and infinitely many solutions that provide excellent operational flexibility for factory manager. We then extract the basis vector spanning the node space to mathematically validate our system using the rank nullity theorem. Finally, by enforcing strict physics non-negative constraint on each product line, we calculate the exact boundary for our product graph and pinpointed the critical intersecting peak. We both free parameters are fully maximized for peak operational efficiency. Thank you.
So here we have our augmented matrix with all four equations and six variables set up. What we do is apply row operations step by step, swapping rows, multiplying, subtracting to slowly clean the matrix up. Each step eliminates one variable from the other rows. After all the operations, we end up with this reduced row echelon form, or RF. You can see the identity light pattern on the left side. This was also verified using MATLAB to make sure our manual calculation is correct. From the RF, column 5 and 6 don't have leading pivots, so X5, which is contours, and X6, which is Mami Kuti, become our free variables, labeled as S and T. That means we can freely choose how much contours and Mami Kuti to produce, and the other four products, Mami Monster, Mr. Potato, Mami Chef, and Double Decker will automatically adjust based on this formula. This is why the system has infinitely many solutions. There's a whole range of valid production plans and not just one. This slide confirms everything mathematically using the rank nullity theorem. Our matrix A has a rank of 4, meaning 4 variables are fully determined. The nullity is 2, which matches our two free variables, S and T. And when we add them, 4 plus 2 equals 6. That is exactly our total number of products variables. This guarantees that Mami's manager have a two-dimensional space of production option to work with, all within the factory's constraints.
To model a real factory, must match reality. The non-negativity rule ensures we never produce negative package. By testing extreme scenarios, we find our absolute operational boundaries from 0 instant noodles up to a peak capacity of roughly 31 cheese drinks and 28 noodles. This defines our structural limits. Here is our boundary visualized. The green polygon represents our safe operating zone. Any production mix chosen inside this area guarantees zero deficits. If we step into the red zone, we hit over allocation, meaning the system lacks the resources to mathematically support it. Stay green to stay efficient. How do we adjust production safely? This null space trajectory shows our exact trade-off using two basis factors. For instance, ramping up instant noodles reduces Monster production by exactly 0.9 units per package. Following this path, lets management pivot targets without breaking system constraints.
Hi, Assalamualaikum. My name is Nurul Uzma binti Burhanuddin, matric number 300708. So now I will proceed to the next part, which is conclusion. To conclude this project, demonstrate how linear algebra can apply in real industrial situation, particularly in MAMIS and logistic management. By using metric representation, augmented matrices, and the Gauss-Jordan elimination method, complex production constraint can be analyzed systematically. The existence of free variables indicates that there are multiple feasible production plans, providing flexibility for managers to allocate resources efficiently. Furthermore, graphical visualization confirm the mathematical results and help illustrate the relationship among variables. Overall, linear algebra serves as a valuable tool for improving production efficiency, minimizing operational inefficiencies, and supporting better decision making in meeting customer demand. So that's all from our group. Thank you.